So let's look at this question from WAEC 2022. It says a lead sphere of mass 5.0 times 10 to the power of negative 3 kilograms is allowed to fall to the ground from a height of 20.0 meters. Determine the 1. Speed of the sphere just before it hits the ground. 2. The Broglie wavelength of the sphere just before it hits the ground. By giving some values for acceleration due to gravity as 10 meters per second squared and Planck's constant 6.63 times 10 to the power of negative 34 joules second. Determine the speed of the sphere. Just before it hits the ground, that's going to be maximum velocity. Let's use our formula for kinetic energy to obtain the speed of the sphere. Right, we have a mass and we have the height. So we could say this is for kinetic energy and this is for potential energy. We cancel out at maximum kinetic energy. M cancels out. We're left with half v squared equals to acceleration due to gravity and the height from the ground. We make v squared instead of the formula. V squared becomes 2gh. And so v is equal to the square root of 2 times g times h. And so our velocity is giving us 2 times g, which is acceleration due to gravity, which is 10 from the question, times height. The height of the sphere from the ground, which is 20 meters. All of that, we're going to find the square root of that. So that should give us 400. The square root of 400 is 20 meters per second. Alright, so that's the speed of sphere right just before it hits the ground, connecting kinetic energy and potential energy. So next up, we have to calculate the Broglie wavelength of the sphere. It's actually used mostly for microscopic particles, and the Broglie wavelength, symbol for wavelength, lambda, that's lambda. Lambda is given by the Planck's constant all over the mass times the velocity. Alright, so the Broglie wavelength is inversely proportional to the momentum. So the Broglie wavelength is inversely proportional to the mass. So the greater the mass for heavy particles, and the Broglie wavelength is very, very, very small. Now, what's our Planck's constant? We're giving Planck's constant as 6.63 times 10 to the power of minus 34 joules second, all over the mass of this particle. The mass of this particle is 5 times 10 to the power of minus 3. That's basically like 5 grams. And then the velocity, we just calculated the velocity from the previous parts as 20. So if you slot that into the expression for the Broglie wavelength, and then point that into your calculator, you're basically going to get our wavelength, the Broglie wavelength as 6.63 times 10 to the power of minus 33 meters.